All right, so we're halfway through our solutions unit. So far, you know what a solution is, right? Solute and solvent, and then you know a variety of ways to analyze it. The most recent way we analyzed it was how much solute can dissolve in a solvent before it quits dissolving, or rather before it becomes saturated, right? You also know what electrolytes are, and again, you'll be looking at electrolytes in lab next week. Today, we're going to ask another very logical question about a solution. We've been very general about taking solute and adding it to the solvent, but what if we were more specific? What if instead of saying, oh, well, you can add this and it dissolves, or you can add this much max and before it quits dissolving, what if instead we actually counted the particles? This is where the numbers will come from and the calculations. Because if I have, go ahead and draw this with me. Oh, forgot to let y'all copy it from home. Pause and copy. Anyway, if I have these two beakers of water, water being my solvent, and I decide to dump in some solute, all right, I got my big shaker here, and I dump in solute, if the resulting solutions look like this, now we're going to assume that those dots are dissolved particles, meaning it's absolutely a solution. Which one of those would you describe as more dilute? Left or right? The left, right? Because by definition, dilute is one that's got less particles dissolved. All right, so my friend here is dilute. And what's the opposite of dilute? Concentrated. Careful, you're getting some of your wires crossed there. This one would be more concentrated. Now, that's not new, all right? We did that in lecture 1. But what I'm saying is, what if instead of saying this one's dilute and this one's concentrated, very general, we actually knew exactly how concentrated each one of them is? And what you would do is you would count the dots, not literally, but molarity is the numerical representation of how strong a solution is. What's interesting about molarity is that all of the labs that y'all have done for me in the back of the room, there's usually beakers with a label on the side that tells you what's inside the beaker, right? That's the way you know what you're grabbing in some of those more hands-on labs. What's funny, though, is that they've always had a molarity written on them. Like whenever you're messing with acid back there, hydrochloric acid, through all your labs during the year, it often says like 3 capital M. You've never asked me about it. I've never talked about it because we haven't done this lecture yet. But I'm actually required by law to write the molarity of that substance on the label, right? The assumption being, what if I have a heart attack 10 minutes later and someone has to come clean my room out? They need to know how strong it is, because these two made-up solutions would have 2 different molarities, strengths, based on how much of the solute's been added, even if they're the same solute. So like when I say hydrochloric acid, that's a strong acid. You know it is because if I bring clay, right? Anyway, yeah. But there's a difference between adding this much hydrochloric acid to water or this much hydrochloric acid to water. They both have the same strong acid in them, but this one would have a higher molarity. And it's represented by a number, which I'm about to show you how to calculate. But it's a very valuable number, all right? I'm constantly having to find, again, the molarity of stuff that I let y'all handle. because there's a certain molarity that you're not allowed to handle. So I have to always watch my calculations as I'm making stuff for you. Molarity is the strength or the concentration, right? You can call molarity concentration, as the slide says, of a solution. The more solute you've added, the higher the molarity is. All right, well, the equation for molarity is molarity equals moles over liters. It's on your slide. And it will be on your formula chart on the exam, not even next week. So we just have to know how to plug and chug. Now, it makes sense to find molarity, which is capital M. It's going to be moles of the solute that you're adding divided by liters of the solvent that is holding the solute. So with that said, let's see what we might be asked to solve. Go ahead and copy down that question, please. We're going to do 3 problems. You're going to copy the questions for 2 of them. In this question, it's giving you a saltwater solution. All right, you've got this solution, and it says that it's the amount of liquid that's in it is 0.3 liters. All right, that's the volume of how much water you poured in. And the strength of the solution is 4.5 molar. The way my M looks, my beaker a little bigger. So the question is, how did you come up with that strength? Well, there would have to be an amount of grams of the NaCl, that's what it's saying in there, that you sprinkled in there. All right, there's this much water. So the question is, how many grams of the NaCl do you have to add to that much water for a chemist to classify it as 4.5 molar? Now, just for general strength, so you know, double-digit molarities are quite high. So if I ever say, hey, this solution is 10 molar or higher, that's a pretty high solution, all right, just so that you have kind of a frame of reference. So 4.5 molar of this solution, that's not as big as it could be. But I also want you to keep this in mind. What is NaCl? It's, well, table salt, all right, because any ionic compound is salt. It's table salt. So I don't want you to think that if you have something with a really high molarity that it means, oh, that's really dangerous. Because yeah, 4.5 molar salt water is fine. Like, you could drink that. All right, but if I gave you 20 molar salt water, well, that's a really high molarity, but it's still just salt water. All right, like you would spit it out the moment you sipped it because it'd be so salty. But I don't want you to automatically associate really big molarities with this will kill me. Now, if it's 20 molar hydrochloric acid, that will eat right through. I mean, it'll eat through the floor if it's that strong. So it still depends on what the solute is. All right, let's do some math though. How do we figure out how much of that was added? How many grams? Well, we have our equation here to help us out. Let's see what numbers we can plug in. Do we have a molarity? Yes. 4.5 molar. Do we have moles? No. You'll notice that nowhere in the question does it give us moles. I don't have a numerator there. Do we have liters? Yes. 0.3. What's the question asking for? Grams. Do you see how grams is not a part of this? The reason this happens with molarity a lot is that grams is the most useful unit in the back of the room, because when you're measuring something out, you can find grams really easy, right? Just put it on the scale. But the equation doesn't have grams. So oftentimes we have to convert between the two. So what we're going to do is find moles. And then it will be a one-step, it's not stoic or anything, a one-step simple conversion to grams. So let's solve for x here. This is simple algebra. I like to put the whole number over 1. It helps you visualize cross multiplication better. 1 times x is x. 0.3 times 4.5 is 1.4. Sig figs is what it is. I have 2 sig figs and 3 sig figs, so my answer's in 2 sig figs. Say it again? Oh, no, you don't. Don't say such terrible things. All right, so now we have a mole count, but it doesn't want moles. It wants to know how many grams of that was added to the solution. So one-step conversion, you've done a million of these. If I have 1.4 moles of NaCl, and I need to convert that into grams of NaCl, drag the diagonal. Grams over moles, so we know that it's periodic table over 1. That should be ingrained in your life by now. And that's why you have a periodic table out. Get a periodic table out at home if you don't have one. Yep. Oh, he fell. I've had to put up new lights and he fell. You've never taken a glass bath before? I get a molar mass of sodium chloride to be 58.44. That's Na plus Cl. Multiply across the top, divide by the bottom, and you will have an answer. And now you can make 4.5 molar salt water at home. Just add 82 grams of table salt to 0.3 liters of water, and that is the strength of your solution.
That is a lot of salt. That's also a lot of water. So
Let's do another one. We'll draw some cards this time. Copy the question. It'll be the last question I make you copy. You don't have to draw these all out, but just for good visual representation, there is now K3P being added into this solution, and it says it's going to add 151 grams of it into a solution. And after it does that, the solution's going to have a strength of 0.0392 molar. Is that strong or weak? Super weak, right? It's not even half a molar. So this is going to be a very weak solution. But if I'm adding that many grams and it's going to be that weak, the question is, how much solvent was in there to make this all true? Now, this question's a little different because grams was given and there's nowhere to put it, right? I have this number, 151, but I don't have anywhere to put it in my molarity equation. So what should I do? Change it to moles, all right? So this time we're doing the change up front. But let's take the 151 grams of K3P and let's turn it into a unit that helps us solve molarity. Moles. All right, I'm going to drag my diagonal. Let's get some help now. Let's go to cluster 2, talk to seat 2. Hey, 2, what number should I put in that square? 1, very good. Wait, do you already have this molar mass? What is it? Can somebody verify that? I haven't added it up yet.
Yes.
Okay, beautiful. All right, so it's moles over grams, therefore grams is periodic table. So 3 potassiums and 1 phosphorus is about 148. All right, let's get some help on this conversion. Let's go over to cluster 2, seat 4. Hey, 2-4, do you have a conversion answer? $1.02? Yeah, y'all like that number? Perfect. All right, yeah, it's got to be 3 sig figs. And sweet, now I have a mole number, which hasn't helped me solve the problem, right? I'm trying to figure out the amount of solvent. But now all of our numbers fit into the molarity equation. The molarity is this tiny number here. So let's go 0.0392 equals. The moles is this number right here. We just found him. And the liters is what we're trying to find. All right, you can put this whole number over 1 and just cross multiply. When I do that, I'm going to get 1.02 equals 0.0392x. We can divide both sides by 0.0392. How many liters is it? Yeah, I get 26.0 liters.
So it is a lot of water.
It's a ton of water. Which makes sense, right? To dilute it to that weak, there's probably a bunch of solvents because it's quite dilute. And we know that by definition, if it's dilute, there's a bunch of solvent. What do y'all think?
It's a little more difficult than sifting.
All right. Y'all try one. Don't copy the question. I mean, unless you think you need to. If you're doing really good at this, just solve it. If you want to copy the question, you can. Now, there is a trick here. Look, look, look. You see that? That's no good. The volume must be liters. The volume must be liters. Now, just change that to liters. It's very easy to do. I gave you a hint on the slide you copied in the dark if you need to remember how to do it. Or talk to a shoulder buddy. Good luck. Did y'all get that? Put it up there. Ruh-roh. Stupid. There's one behind you underneath the road map. Sorry, I'm trying to get it back up. If you get stuck, call me over. It gives me grams, which is no good. So I'm going to take the 120.4 grams of nitrogen dibromide and change it to moles, which can fit into the molarity equation. Drag my diagonal. We've got moles over grams, which is going to be 1 for mole and PT for grams. I should have added this up. 1 nitrogen plus 2 bromines. Do you get 173.81? Multiply and divide to get a mole count to 4 sig figs of 0.6927.
Just round up to 0.7.
No, 4 sig figs. Come on, man. All right, the question says, what is the molarity? So we're just flat out solving for big M. Moles over liters, 0.6927. Over, now here's where you got to be a little careful, because it gave me 376 milliliters. 376 milliliters. The unit's getting bigger, so the number should get smaller. Yeah, that rings a bell. How many slides is milli? It's 3 slides, right? It's 1,000. Milli's 1,000 times smaller. So we need this to get smaller by 3 slides, so it's 0.376. And that will get you to a final answer of something. .84 molar is the best way to say it.
So it's just like if you were drinking like a mild spice.
Well, you don't know what nitrogen dibromide is. So I mean, if it's cyanide, any of it, I mean, 1 molar cyanide would kill you.
Well, that's not something.
I know, but you don't know what it is.
As a bromine. So.
Questions? That's all I got for you. Hey, it's not all I got for you. What's tomorrow?
Ice cream.
Tomorrow's ice cream day. Raise your hand if you're going to mess it up. If you are on this list, be awesome tomorrow. Bring me milk in the morning so you don't have to carry it around all day and let it go bad. Oh, still recording.
That was
Ice cream day.